Hi, everyone. Welcome to the CSHS webinar, Field Methods. It's 11 a.m. Mountain Time, and we're just going to wait another minute or so for everyone to log on. Okay, I think we'll get started. Can everyone hear me? Perhaps a nod from our, okay, thanks. Welcome everyone to the CSHS webinar on field methods. This webinar is offered in collaboration with the CWRA Manitoba branch in lieu of this year's national conference. My name is Emily Anderson, and I'm your host today on behalf of CSHS. Before we get started, I'll take a quick moment to introduce the CSHS and our mandate. CSHS is the Canadian Society for Hydrological Sciences, an affiliate organization of the CWRA, the Canadian Water Resources Association. The goal of the society is to promote the science of hydrology and its sound application in effective water management. We do this by offering a number of courses each year. We support modeling tools, including Grey J and the Hydrology R package. We also host webinars such as this one. We take part in the National CWRA Conference every year and are also involved in providing awards and scholarships. You can learn more about what we have to offer at cshs.cwra.org. To get involved, you can join our mailing list, which you can sign up for at our website. You can become a member of CSHS, or you can volunteer with our organization. Before we get on to our presenters, I have just a couple more housekeeping notes. We have an hour booked for this webinar. Each speaker will present for 15 minutes, followed by 5 minutes of questions. Participants will be muted by default. We encourage you to ask questions in the chat window, and I'll field as many of these as possible. The webinar is being recorded and will be available in a few days at the website on the screen. And you can find our past webinars there as well. So with that, I'll pass things off to Vincent Cormier from WSP, and he will present on streamflow data acquisition in remote regions and how that can improve hydraulic design for highways. So we'll just share Vincent's screen.
Yeah, okay. Do you see it?
Yeah, all good.
Okay, perfect. Okay, well, thank you for having me. Really glad to be here today. So I'm a hydrotechnical engineer at WSP, worked in Quebec for a number of years, and now I've been transferred in Vancouver. And today I'll present the result of one of our projects we completed with Parks Canada in the Kootenay National Park, titled Streamflow Data Acquisition in the Kootenay National Park. I shortened the title a little bit because it was too long, in my opinion. So here it goes. So today we'll cover the context of the study, the main objectives, the main challenges we faced during the project, the field investigation we completed to address those challenges. I'll share with you the main monitoring results, and finally I'll share the findings and the highlights of the study. So the Kootenay National Park, for those who've never been, it's in the Rockies, Canadian Rockies, right on the border with Alberta and BC. It's about 2 hours away from Calgary, and it's really pretty. If you have the chance just to go there on vacation, I highly recommend it. You can access the park through the Highway 93 South, which is the main assets of Parks Canada within the park. So the Kootenay National Park, being in a remote environment, it is exposed to natural geohazards, mainly debris flow and debris flood, bank erosion, wildfire is a big one. They had two big wildfire seasons in 2003 and 2017, like much of BC. And flooding is another potential geohazard, even though in recent years there's not been any documented major flooding issues on the highway and within the park. But bank erosion is an active problem. Just trying to move this here, maybe. Okay. Yeah, so bank erosion is a problem, and Parks Canada need to intervene on a yearly basis almost to repair the highway at certain location. So Parks Canada wanted to know if those geohazards could be influenced by climate change and how. So the project is a broader study that is titled Kootenay National Park Geohazard and Climate Risk Assessment. It was funded by the TIRAP program. And the main objective of the study were to determine projected stream flow patterns within the park on the Vermilion River and the Kootenay River, where and how this will affect patterns of erosion, whether bridges and structural culverts are at increased risk, and when these assets are most likely to be impacted in any given year, and how we can monitor it. So that's the broad scope. We won't go over all of this today. Today we'll really focus only on the field investigation we completed to fulfill those objectives. Okay, so the key challenges we faced, the first one and the main one is that it's a remote location. So there's not much data source from a hydrological or hydrotechnical standpoint. And historical geohazards events are poorly documented. Being remote, some events went unseen or under the radar. So it's hard to know the historic of the highway and the park. The second one is that it's at a high elevation, sometimes above 2,000 meters of altitudes. So we expected significant orographic effects, so more precipitation at higher altitude. And the baseline conditions were not well defined. So what is the hydrological regime of the main rivers within the park in current condition? And the other big challenge that it's a broad study area. The park itself is about 1,400 square kilometers. So to identify assets at risk at a fine scale, such as culverts and bridges, or even some small stretch of highway that could be impacted by erosion, was quite a challenge. So in terms of hydrology, what was available at the moment of the study within the park? Well, there was two hydrometric stations, one on the Vermilion River and one on the Kootenay River. The one on the Kootenay River is still active. It's been online for quite a few years, since 1939. And at the hydrometric station location, the watershed area is about 416 square kilometers. It has a mean elevation of 1,837 meters. On the Vermilion River, the station is unfortunately inactive, but it had a period of record of about 10 years between 1946 and 1956. At that location, the watershed has an area of 951 square kilometers and mean elevation of over 2,000 meters. So the Vermilion River was the main focus of the study because most of the erosion issues that were observed in the park in the past decade most of them were observed along the Vermilion River. And so we tried to compare the yearly peak flows between the Kootenay River and the Vermilion, just to see if there's any opportunity to extend the period of record on the Vermilion River. But when we checked the chronological pairing, the fit wasn't great. So they displayed different unit discharge and just different timing. So ranking pairing could have provided better result, but still the fit wasn't too great. So within the park, the hydrological regime of the Vermilion River and its tributaries was hard to determine in current day present condition, so let alone in projected condition. So we then had a look at the regional hydrology, wanted to know if there's other hydrometric station in the area that could be used for regional analysis or single station basin transfer to better understand what kind of peak flows the Vermilion River and its tributaries can experiment. And the first thing we looked at is the published 10-year flood event that we divided by the watershed area just to have unit discharge, and we plotted that against the area just to see if there's any kind of trend between the watershed area and the unit discharge. And we can see that there's no clear trend. The data is really scattered. And in the park, most of the watershed have an area between 10 and 1,000 square kilometers. So looking at this, it's really hard to pick individual station to do a regional analysis. It's too scattered. And when we looked at the same data but plotted against the watershed average elevation, instead we can see a clearer trend. So as the average elevation increases, the unit discharge increases, confirming that there's a strong orographic effect in the region. But once again, it's pretty scattered and pretty hard to pick the right station that represents the hydrological regime in the park. So in terms of regional hydrology, we felt that there was a gap there and a lot of uncertainty with the available data. So to address those, we established a kind of a workflow, and that is the kind of the broader workflow we used during the study. Today we'll just go over the red boxes. The blue boxes were kind of the next step of the study. So we started by doing continuous water level measurements on the Vermilion River and two of its tributaries. At each of those locations, we built ECRAS models in 1 dimension or 2 dimension, depending on the river characteristic at those locations. The goal of the ECRAS models were to extract rating curves, relationship between water level and flow, to then develop flow hydrographs over the period of record, and then trying to develop correlation analysis with other active hydrometric stations in the area. Once we developed correlation, we analyzed projected stream flow data published by the PCIC with the VIC-GL model, and the impact of climate change were then included into the geohazard risk assessment for erosion, flooding, wildfire, and debris flow. So if we look at one example, I've picked the Vermilion River at Numa Falls. So it's within the park. It's really close to the Highway 93 South. So what we've done there, it's really similar to what we've done to the 4 other sites. So we installed 2 data logger, 1 level logger in the river and 1 barometric logger to correct the water level that were measured. We then surveyed 10 cross-section. At each cross-section, we measured the water levels. And using an ADCP, we then performed 2 flow measurements at different flow value, one at low flow to capture all the hydraulic control in the river reach, and one at higher flows. So both flows were used to calibrate the ECRAS model. So if we look at the different steps, once we gathered all the data on the field, we built the ECRAS model. In this case, it was a 2D model. And then we extracted the rating curve at the level logger location. So water level function of stream flow. The idea was to use that rating curve to extrapolate the flow values above the one that were measured at the site. We then processed the water level that were measured at the bottom left here on the figure. So we measured water level from November 2018 to August 2019. The idea was to capture the 2019 spring freshet. And in the winter months, there's a lot of noise in the data. It's mainly due to the ice cover that affected the results, but it's really the flood condition that interested us. So from April to late August. So by applying the rating curve on the water level that were measured, we were able to develop a flow hydrograph during the period of record between November 2018 and August 2019. So in the case of Numa Falls, you can see that the river peaked at 35 cubic meters second. We then tried to establish correlation for the 2019 spring freshet. And so we looked at various active stations in the area, and the one that had the best fit was the Kicking Horse River. It's a watershed that is just adjacent to the north of the Vermilion River watershed. It has a bigger watershed area of 1,850 square kilometers, but similar watershed slope and slightly lower mean elevation. And you can see the flow hydrograph for the 2019 spring freshet at the Kicking Horse River is really similar to the one we obtained for the Vermilion River. They both peak at pretty much the same date on June 2nd, almost at the same hour, and all the subsequent peak during the summer, they all match fairly well. And we had 3 flow hydrographs on the Vermilion River at 3 different sites, and they all displayed similar characteristic, and they all fitted really well with the Kicking Horse River. So just by applying the single station transfer equation on the left with the original exponent of 1, we managed to take the Kicking Horse flow hydrograph, transfer it to Numa Falls, and compare what we obtained from field measurements and modeling. And we can see that the fit is excellent. It works really well. And we observe the same thing for all sites. So even smaller tributaries of the Vermilion River, they reacted exactly the same than the Kicking Horse River. One of the big advantage of establishing that correlation with the Kicking Horse River, it was monitoring. So the park being really remote, for Parks Canada, it's not necessarily easy to send a field crew to inspect all the highway that's over 100 kilometers to see if there's any problem somewhere. So we analyzed all the past erosion events within the park. We compare them with the flow that was attained on the Kicking Horse River, trying to establish erosion initiation threshold. So when that threshold is exceeded, that erosion could be initiated. And we ended up with a threshold of 200 cubic meters second based on historical events. And during the following years, so the past spring freshet in June, on the exact day that the threshold was exceeded, they had 2 major erosion events on the St. Clair River and one of its tributaries. So it gave them a bit of confidence with the tool and makes it easier for them to know when they should send crews to inspect the sites that were identified to be most at risk. So to conclude, the key highlights of the study was to develop flow hydrographs at 5 locations within the National Park, and then to develop correlation with the Kicking Horse River that could then be used to better understand the impact of climate change by picking the right station from the PCIC published data to determine peak flow magnitude change, frequency change, and timing change in the National Park. And finally, we determine assets at risk in current day and projected condition in the National Park. So that's it. Thank you for listening. And this is my favorite picture of the park. You can see that if you go on the Vermilion crossing within the park. Thank you.
Okay, thanks so much, Vincent. We have a question from Rob Chlumsky, and he says, was there a way to consider ice effects in the 2D model for developing that rating curve?
If there
Would there
was
be,
what, sorry?
it's a two-part question. The first part is, was there a way to consider ice effects in the 2D model for developing the rating curve?
Oh, well, it could have been, but in our case, we really focused on the spring freshet, which was unaffected by ice. So we were not interested really in making sure that the model was accurate during when there was an ice cover on the river. So there could have been one, but we just didn't look into it.
Okay. And the second part of the question was, or is, would there be any limitations on using the rating curve based on the season and ice cover conditions?
Yeah, definitely. Like the rating curves, they won't apply if there's an ice cover on the river. So they're only applicable when you're ice free, and yeah.
Okay. There's a couple more questions coming in. Julia Bond asks, how do you determine erosion initiation threshold?
Yeah, that's a good one. So what we knew is we didn't have much. We had pictures of erosion events that occurred in the past, and we knew the date it occurred. The date it exactly initiated is a bit, it's based on testimony from Parks Canada crew. So there's some uncertainty, but we just look at the flow hydrograph for the corresponding date and when the erosion issue was thought to be initiated. We looked at the associated flow in the Kickinger's River, and we didn't want to use that as an exact. It was more a tool for parks to know when to send crew on field, rather than determine really precisely based on river characteristic when the erosion could be initiated. So it's more of a tool than an exact model that could predict exactly the time it will begin. But to answer that question, it's really based on historical events.
Okay, thanks. One final question from Xavier Pinto. Your rating curve was a theoretical curve extracted from HEC-RAS. Normally you would need to use 10 points to develop a rating curve. Do you think you would have got better results following this approach rather than the 2 points that were used?
Well, yeah, for sure. I mean, the model could have been calibrated better if we had more measurements. But the thing is, so we had a schedule that we need to respect due to funding. We had a budget also to respect. So we didn't have time and budget to do a lot more than that. We tried to have a flow measurement at higher flow to improve our confidence in the models. But we kind of tried to improve our confidence by having several sites on the same river, just to see if there's some repeatability in the unit discharge that were obtained, and there was. So the idea was to try to do something with a budget that was available to improve our understanding of the hydrology in the park, rather than just trying to rely on existing hydrometric station.
Certainly. Okay, thank you so much. There are a couple more questions coming in, and I would just ask those participants to contact you directly, Vincent, if that's all right with you.
For sure, yeah.
Okay, so we'll move on to our next speaker, Jimmy Ehrman from the University of Manitoba, who is presenting on ice roughness estimation by photogrammetry. So we'll pass the controls over to Jimmy and let you get started.
All right. Okay, sharing my screen. Where does that go? Screen 2. Okay, is that making it out to everyone?
That looks good.
Yeah, okay, cool. All right, thank you all for being here this afternoon. Today I'm presenting my research on ice roughness estimation via remotely piloted aircraft and photogrammetry. So in northern climates, river ice can have large negative impacts on water resources. These include things like reduced hydropower generation, damage to infrastructure such as bridge piers, and flooding throughout the winter, but especially in the spring. And ice roughness is one of the main determining parameters for the severity of flooding. And it's a really important parameter in hydraulic modeling if we're considering flow through the winter. However, ice roughness is really difficult to estimate. One relationship put forward in 1964 by Nezikovsky relates ice thickness to ice roughness. And it's a really good first cut. It's widely used in engineering, but it's based on a limited data set and only on rivers in Russia. So its wider applicability is in question at times. More complicated methods include back calculation of ice roughness through hydraulic models. So if we know water surface elevation and flow, and then other characteristics of the river, we can back calculate the roughness that would be required to produce those observations. Finally, we can send technicians directly out onto the ice if it's safe enough. So we can cut a hole in the ice, measure the velocity profile or flow, and back calculate roughness that way. Or I've even seen it done where people will cut a chunk out of the ice, flip it over, and take measurements of the roughness just using a ruler. So both of those methods are pretty slow and they can be quite risky and just frankly impossible in some situations. But what's a better way to approach this problem? If we could find a way to safely and accurately measure the surface of the ice and infer roughness that way, would it be able to tell us anything about the subsurface ice roughness? And that's the main question that I'm hoping to answer with this method and this research. So remotely piloted aircraft, or RPAs, or drones as they're most commonly known, have been widely used in topographic surveys, and they've recently become much more accessible to the general public. Transport Canada has recently streamlined the licensure process for drones, and it's quite simple. The drone that we use is a basic consumer grade drone. It collects 4K image stabilized video right out of the box and costs, I think, under $2,000. So it's a lot quicker, it's a lot safer, and like recently the technology has become a lot better. Just wanted to show a quick example here of what's possible with some of the drones. So this is a video that we collected using our drone. We're hovering about 10 meters over the water surface, and we can see ice formation happening, which is a perspective that we really couldn't have even a few years ago. A helicopter would have been too expensive for us and for a lot of other researchers on this sort of scale. Satellites don't have a high enough resolution, and we just can't see this kind of detail from the banks. So it's really opening up a new avenue for observations for us and in a lot of similar fields. So coupling drone aerial imagery with photogrammetry, we can produce a 3D surface model of our study area. Photogrammetry uses changes in perspective and common points observed across multiple photos to infer distance from the camera and from the camera to the study object. So it uses parallax error, which is similar to how your eyes perceive depth. And as long as each point of interest is viewed in at least 2 images, it can be used in the analysis. For this research, we use Agisoft PhotoScan Professional, which automates a lot of the process for us. And if we throw in all of our drone photos and some survey data, it can produce a geo-rectified surface for us. RPA photogrammetry has already been widely used in materials estimation and post-construction monitoring, and it's even been used for roughness studies, although so far only in the evaluation of bed roughness of gravel rivers. But how accurate is this method in our application? We have a field limitation where we can only place our geo-rectification targets on the left-hand side of our study area. This is because the whole point is to reduce risk to our field staff, so we don't want to send them out onto the middle of the ice to lay down targets. So to test if this bias had any impact on our data, I flew the drone over a field somewhere where I could place targets uniformly throughout, and then ran the photogrammetry algorithm comparing a scenario where I used all of the targets versus a scenario where I used just the targets grouped in a similar fashion as we would on our study sites. And we did find good agreement between the two. We had a roughly 3 centimeter vertical error on the typical target scenario when compared to independently verified GPS points. So we're applying this method now on the Dauphin River, which is in central Manitoba, 300 kilometers north of Winnipeg. The Dauphin River flows for 52 kilometers from Lake St. Martin and into Lake Winnipeg, the last 15 kilometers of which is really steep for Manitoba at 0.15%. You can compare that to the slope of the Red, which is, I believe, about 0.001%. So that extra grade gives us a lot of really interesting ice dynamics, which is great for us. It's been heavily monitored for the last 5 years. All the stations marked in the little inset on the map there, marked with a DRLL, are locations where we have a continuously logging water level logger. We also have a continuously operating meteorological station. And right around this time of year, we'll be going out to perform ice formation monitoring. And then later on in the year, we do an ice elevation survey. Coupling this with our aerial imagery, this makes the Dauphin River one of the most heavily monitored fluvial ice monitoring sites in the world. So we have our aerial images, we have a good quality georectified 3D surface, but this is a huge data set, sometimes more than 150 million points. How can we simplify that down into a single roughness value that sort of represents that ice surface? I began by taking a 50 by 50 meter subset from the center of the river, but even in this subset, some of the variations in topography are not just due to roughness, but are caused by things like the slope of the river and bowing in the ice cover caused by receding water levels. To address this, I applied a linear model to adjust the absolute value and slope of the test surface to roughly 0, and then further applied a 2-dimensional Fourier transform with a bandpass filter to eliminate some of the very highest and very lowest frequencies, which I associated with noise in the image and other large-scale topographic impacts. From here, the surface data were grouped into 3 categories for statistical analysis. The first category is raw data, which would be the original subset with no filtering or adjustment. The next would be that same data set, although with the filtering and adjustment having taken place. And finally, the peak data, which is a subset of the general data, corresponding to only the peaks found in the surface. So looking at the example subset on the right, there's a transect T taken through the top, the profile of which is shown below. And I've got a few points marked off there, identifying some of the peaks and some of the general data. But the key takeaway here is that our general data set already incorporates all of the peak data, and the peak data is just a subset of that general data. So from here, there were 6 roughness height characterization methods, which were tested based on a literature review. This includes the interquartile range and standard deviation of the roughness heights. So those 2 metrics were applied to the entire general data set. And then the minimum, maximum, average, and 84th percentile of peak values were also taken off of the peak subset. And all of these values became then the D value in the modified Strickler equation on the right. So that's a representative roughness height. And then when multiplied through the equation and with hydraulic radius, the result is the Manning's N for that ice cover. So we've got these 6 metrics. How do we then test them to see if they're any way representative of our surface? Well, we used inverse hydraulic modeling. We've got good instrumentation and historical data on the site, including water surface elevation, flow, and quite a few ice thickness measurements. So I constructed a simplified 1-dimensional attestation model based around Manning's equation. So just a really basic cross-sectional approach to sort of the hydraulics there, where we're plugging in the water surface elevation and just finding out which ice roughness is required to match the observed flow. So how did this compare between our modeled results and our observed results? I've got here the 6 plots showing the 6 different roughness metrics and a nice one-to-one line where I hope my data will be plotted on. And you can see that it's not quite making it there. There's quite a bit of scatter, but there's also correlation here. So we did see a generally increasing trend where sites that were observed to have a rougher surface ice were also predicted by the model to have a rougher subsurface ice. The 84th percentile and mean of peak values, which are in the bottom right, just by visual analysis seem to do the best. But it's also interesting to note here that the max peak value seemed to do the worst. So it had an even different kind of scatter to the data as compared to many of the others, which were very similar, and is, I think, quite a bit off. But how about comparing this to an even simpler model? So I mentioned earlier the Nezikovsky relationship, which relates ice thickness and roughness. And I've got the same set of plots here with the same 6 metrics, but the y-axis has been replaced by the Nezikovsky predicted roughness rather than the modeled roughness. And the x-axis is still on our observed roughness. So we see a lot tighter relationship with the data here. And it's, I think, interesting to see that the max peak value, which did so poorly previously, is now plotting almost entirely on the one-to-one line, which is awesome. But I would hesitate to say that the max peak value is now the value we should use as most representative, because this would be pretty heavily influenced by outliers in future data sets. But just again, looking at it visually, the 84th percentile and mean peak values seem to have the best fit. It's also interesting to note that any relationship here between the Nezikovsky roughness and the surface roughness may indicate a link between the surface roughness and ice thickness, since the Nezikovsky relationship is based solely on ice thickness. Just moving on to some more observational results. From some of our 3D surfaces, about 3 different forms of ice roughness were observed. So the first in the upper right corner is generally termed rough ice, which was mostly observed in the turbulent sections of the river and seemed to be composed of crushed and stacked frazzle pans. And you can see on the profile that is quite rough. The next type of roughness down, we call it smooth roughness. It's formed mostly in slower flowing sections of the river, composed mostly of thermally grown border and skim ice. And finally, at the end, we see ridged ice, which seems to occur mostly in smooth sections where there's been a lot of pressure on the ice, and different sections of the ice cover are cracking and crushing and forming these ridged forms of piles of ice. And you can look just at the sort of profile at the bottom on the right there of the ridged ice. You see that the roughness elements are on the order of 60 centimeters high, whereas even in the rough case, they're just a little under 20 centimeters. So it's quite dramatic with these ridged ice formations. So these different categories seem to also exhibit different statistical characteristics as well. So I've got the same 3 categories, rough, smooth, and ridged, laid out here, and just example distributions from each. So I noticed mostly that the rough ice tended to have a kind of more smooth, almost normally distributed looking profile, whereas you compare that to the smooth ice surfaces, which had a lot higher, a lot more peaky values with a higher kurtosis. And I would expect this of a more uniform surface where most of the roughness height values are grouped more around the mean rather than being spread out and distributed. And then finally, the ridged ice surfaces showed the most abnormal distribution. And in some cases, those distributions were nearly bimodal. And I think this makes sense when you consider that the ridged surfaces would be these bands of very rough ice kind of superimposed on a smooth surface. But none of the distributions tested were past the Shapiro-Wilks normality test, so none of them are normal, in fact. So in conclusion, we tested the RPA photogrammetry method, and it seemed to perform very well in winter field monitoring of fluvial ice covers. It could produce accurate 3D surfaces of snow and ice. And our modeling approach was maybe perhaps a little simplistic, as we didn't get great matching with our observed roughness, so it's hard to tell which in fact was in error. but the observed roughness values compared very well to the Nezikovsky roughness. The 84th percentile of peaks and mean of peaks seem to do the best job of fitting the different roughness methods. And there's an implied possible link between surface roughness and ice thickness. So in future work, I think we could improve this by having a more robust hydraulic model put in place. But again, the ice hydraulic modeling is an evolving field, and this would be quite a lot of work. So I'm not sure exactly when that will happen. But like any study, this could benefit from a bit more field data to help us flesh out the relationships. I think we could have further testing of the relationships between ice thickness and surface roughness. But really the field is wide open for additional developments in ice surveying methods using RPA photogrammetry. I think there's a lot more to explore here. I'd like to acknowledge that the bulk of this research was conducted on the traditional lands of the people of the Dauphin River First Nation under Treaty 2, and with generous funding from NSERC and Manitoba Hydro. And research guidance was provided by my supervisor, Dr. Sean Clark, and a lot of the field work was planned and had a lot of assistance from Alexander Wall. With that, I'd like to thank you all for your time and attention, and I'm happy to take any questions now or at the end.
Thanks so much, Jimmy. I have a question about the software that you use for processing. Just how I believe you said it was Agisoft.
That's right.
How did you select Agisoft, or did you test different software, consider proprietary versus any open source?
Right. We did not test any different softwares. Agisoft was just the one that we had a license for, I guess, and they are quite expensive. So we're just using the one that we had, but there are a few papers out there that I came across where they did compare things like Agisoft to Pix4D to sort of research grade photogrammetry algorithms that were built in-house. And all of them had various pros and cons, but I think the conclusions of the paper were that almost any of them were successful. And I think it was Agisoft that seemed to have, a lot of people were remarking on its defaults. So the default values that it picked for a lot of the sort of bundle adjustment and tie point limiters and all like very technical elements seem to be very well chosen.
Okay, thanks so much.
Mm-hmm.
And just one other question. Oh, we're getting a few more questions now. Maybe we'll just do one more, and then any that aren't answered, you can contact Jimmy directly.
Sure.
Edward Hunt asks, oh, there's a bunch now. How did the presence of snow on the river impact ice research or the application?
Right, yeah, so that is definitely a big factor. But the result of that is that we have to be out there taking our photogrammetry data pretty much as ice formation is happening and kind of at the point where we expect final ice formation to have locked in for the winter. Of course, any snow on top is going to obscure, it's going to fill in the valleys, which will impact how we calculate, or the results of the calculation of things like peak to valley distance or even the max peak, because it'll adjust your average. We did end up having a few data sets that were from later on in the winter with snow cover, and they surprisingly didn't vary as much as I thought they might. But definitely from a theoretical standpoint, you'd want to be out there pretty much the day it happens.
Okay, thank you so much, Jimmy.
Yeah.
Okay, our last presentation is James Baumhoff from the Water Survey of Canada, presenting on streamflow measurements using image velocimetry. So we'll pass it off to James.
Thank you, Emily. Just give me a second to make sure that I see everything. Okay, can people see my presentation?
Yeah, looks good.
Perfect. Well, thanks to the other two speakers, Vincent and James. Those were really interesting and relevant presentations to, I think, also what I'm going to be speaking on. So my name is James Baumhoff. I work for the Water Survey of Canada, and I'll be giving a presentation on image velocimetry today. So I'll get right into what I hope to talk about and the questions I hope to answer. First, I'll give an introduction to what the Water Survey of Canada is and what we do. And then secondly, what is the problem with how we currently measure flows in rivers? And then lastly, a series of questions. What is image velocimetry? How does it work? And how could it be useful? So the Water Survey of Canada runs Canada's National Hydrometric Program. Rivers are a provincial jurisdiction, and so this program is run with the provinces and territories as partners to the program. And we operate about 2,200 gauging stations across the country, which anyone who knows, who's done any studies like the ones we saw, knows still is not enough, and we never have the one at your site, unfortunately. But this is done through 30 offices across the country and with about 220 field technologists. And so I work for head office, and our job is to support the field technologists. And so just while we're looking at those numbers, it means that a technologist is in charge of about 10 stations. So that gives you an idea of how long it takes, to get out to site and get that data looked after. So how is flow normally measured? This is a the typical way that flow is measured through a stage discharge curve, which Vincent already talked about a little bit. So on the left side, we have just a side view of a stream, and we'll pick a section of a river or stream that is nice and stable and has a good downstream control. So a great downstream control is a weir, and that will cause the water to back up with subcritical flow. And then we can put a stage sensor in there that continuously measures the stage. Then we can go and take discrete measurements with either a flow tracker or an ADCP and plot those discharge measurements on a plot and find the corresponding stage for that as well. And then we can create a stage discharge curve using the actual measurements. And then when we monitor flow, we can just take that, when we monitor the stage, we can take that stage and find the corresponding discharge. So that works for most of the stations for most of the time. However, there's always examples where it doesn't work, in cases where it doesn't work. For instance, ice jams that form downstream will cause the water to back up. This happens every spring and often many times a year at stations. So when the water backs up, you'll get a corresponding stage for the same flow, and that will plot above the curve, which gives you an error of your discharge. And so this is a typical hydrograph at a station during freshet. On the x-axis, we have time, which is in days. So it goes from basically March 9th to March 23rd. This is at a station nearby Ottawa. And the blue line is the stage sensor that is continuously sensing. And then the red line is the corresponding discharge that's calculated through that stage discharge curve. So when we have an ice jammer that causes backwater, how does technologists actually figure out whether backwater is occurring when they're not actually on site? So one of the most obvious ways is that when they're looking at the stage trace, they can see how jumpy it is, which is an indicator to show that ice jams are forming and releasing, forming and releasing. And so this would show that at least while the hydrograph is climbing, that backwater is occurring. But after that peak occurs, that trace smooths out, and that combined with looking at temperature data to show that it's warming, it makes it very reasonable to conclude that the backwater has disappeared. However, we went out and actually did a ADCP measurement after that peak, and that ADCP measurement gave us a flow that was about half of what the rated discharge was. And so that's the error in the discharge on the hydrograph. And if we extrapolated what that actual peak would look like, it would again be about half of what we saw. So that's great if you could get out to site and do a discrete measurement, but a tech has 10 stations to look after, so they can't go every day and take those measurements. And so the next question is, when does this backwater stop? How long would you apply a correction for? Would you go to this trough, or would you go to the next peak? Would you go out another month? You can look at temperature data and the trace, the stage trace, but you really don't have, you really need more information. And so these conventional measurements, they're often expensive and risky. Often the sites are remote and require helicopter fly-in, and so they're infrequent for that reason. And then also just timing, it's difficult to get out and get your measurement at peak discharge. And that's where there's potential for image velocimetry. So what is image velocimetry? It is estimating surface velocity from a sequence of images and then using that surface velocity to estimate discharge. So you can get the sequence of images through a variety of sources. James talked about the benefits of drones, and we're investigating that at Water Survey and see a lot of benefit as well. They provide very high quality images that are very valuable. You can also get them through fixed cameras on site mounted to a gauging house. So this is just typically a security camera. And one of the benefits of that is we can remotely trigger those videos. And then you can also just go out and take a cell phone video. And the benefit of that is everybody has a cell phone, so it's very easy to get a video. So there's 7 main steps in estimating discharge through image velocimetry, and I'm just going to go through those now. So the first is to select a site. Really, you can select any site that has a stream flowing through it. These are some of the test stations that Water Survey is testing out. We've done some concrete channels and then also natural sites. As a general rule of thumb, if you take a video and you can't see particles moving on the water or the surface texture, you can't see the water flowing, then it's not a good candidate for image velocimetry. The next step is to survey ground control points and cross sections. So ultimately, it's a velocity area method. So the bottom image shows some people surveying the cross section of your river. And then you also need some ground control points. If it's from a drone video, something as simple as just laying a survey rod on the ground will get you ultimately you need a way of converting pixels into actual distances. And for angled images, you typically want multiple ground control points and those surveyed. So you have your X, Y, and Z coordinates. And then the next thing to do is record a video. So Carter already mentioned the methods to record those videos. You basically need to capture the stream and those ground control points in your field of view. And then you orthorectify the video. And that's just basically translating the images or the video into real world coordinates so that if you draw a line on the image, you can find the actual distance. And so that you can do 2D or 3D orthorectification. And James talked about some high-tech software that can do that. And then the key step is to extract surface velocities from those images. So there's 2 main methods of doing this, and I'm going to talk about this a little bit more in detail. So the first thing you do is you take your video and extract all the images out of the video. You know your frames per second or your frame rate, and so you'll know your time between all those images, and that's your delta T. So the first method with large-scale particle image velocimetry, or LSPIV, is to look for patterns on the surface of the water. So in image A, you've got your blue box, which is your search area, and you're going to find a pattern in that search area, which is the orange box. And then you're going to go to the next image, and within that search area, look for that same pattern. So it looks in the lower left, doesn't find good correlation with that pattern. Lower right doesn't find good correlation, and then goes up and finds good correlation where that B boxes. And then all you need to do is draw a line between the two centroids of image A and image B, and you have a distance. And because you have delta t, then you have a velocity. So this is an example of a site nearby us where you can see the pattern of particles in image A has translated or moved downstream in image B. And so all you do is find that correlation, and then you've got a vector drawn in between there. So you have software that does that hundreds or thousands of times, and then you've got a velocity field on the surface of the river. So the next method is what's called space-time image velocimetry. And I've shown here's a video of a cyclist. Imagine the cyclist is a particle flowing downstream, just to show you how the method works. So similar to LSPIV, you extract your frames. This video is taken at 2 frames per second. And then you've also orthorectified your image, so you have a distance. And the way it works is you draw a line along your likely flow path of a particle and extract those pixels in each frame. So this first row here is the flow path for frame 1. And then the second one is the flow path for frame 2, frame 3, frame 4, frame 5. And so what you're left with is a space-time image where you've got time on your y-axis, because those are the different frame rates, and you've got space or distance on your x-axis. And you'll notice the cyclist is moving down at an angle, and you can just plot that or draw a line through that path and get the slope, which then gives you velocity. So in this case, the cyclist was going about 5 meters a second. And so you can do that on a river where these lines are all the flow paths of the particles, and you extract a space-time image for each one of those lines, and you can just draw the slope or have an algorithm figure out the slope of those particles, and you get a velocity at each one of those lines. And then you have velocities across your whole stream. So now you have surface velocities, and what you really need is depth average velocities. So there's some papers out there. You basically use data from ADCPs and flow trackers to calculate an alpha value that you apply to your surface velocities to get your depth average velocities. And then after that, you have your area from your cross-section survey. You have your depth average velocities, and then you just do a regular velocity area method, and you integrate that across the river to get your estimated discharge. So these are some of the softwares we're testing. The two on the bottom, I'll point out, those are LSPIV softwares, and those are free to download and use. So FUDA, LSPIV, and River. So if you're at all interested, I would say go download those and try those out. We're also looking at software called HydroSTIV, which does the space-time image velocimetry, and then one called FOTRAC. And then we're also working with the University of Ottawa to develop some optical flow methods as well. So if we go back to that scenario I had at the start, we're asking the question, when does the backwater stop? And we have that one discrete measurement for the ADCP that shows that there's backwater, but we don't know how far that should continue. Well, at this site, we've triggered videos each day from a fixed camera and done the image velocimetry analysis, and we got discharge from all those videos. So this could be done every hour. This particular example was done once a day. And you can see that the image velocimetry discharge estimates match the rated discharge around 4 days after when we initially thought. So now we have a solid answer as to when that backwater stopped. And then the other thing to note is that the peak flow was much lower than what the stage discharge curve showed. So image velocimetry can really add a lot of value to the gauging station. So in conclusion, we've seen that image velocimetry works, and Water Survey Canada is validating and refining these methods. I've basically just shown you a prototype. There's a lot of problems that I didn't show, And it's still very much in the prototyping phase, but I'm optimistic that it's a very good method. And it has huge potential for remote measurements. Instead of having to take a helicopter to fly a site, you can just trigger a video and get a decent flow estimate from there. And then also on-site measurements when entering the water is too dangerous. You often want your flow measurements at your high flow, and that's when there's lots of debris flowing down and it's dangerous to get in the water or even put a boat in the water. So that is all I have, and thank you for your time. My email here is here on the bottom, so if you have any questions or comments, feel free to email me, and I'd be happy to take any questions.
Thank you so much, James. We do have a few questions. We're just coming to the top of the hour, so maybe we can fit in one question, and then the rest of the folks can contact you directly. We have a question that asks, how would this compare to using a stationary side-looking ADCP? With a stationary ADCP, you could get a handle on backwater and other unusual conditions affecting your reef curve.
Yeah, great question. So, like you said, a side-looking or up-looking ADV would also be a great candidate. One of the benefits is that you're not actually going in the water or putting an instrument in the water, so there's less complications with that. And so I wouldn't say one is better than the other, but it's your circumstances. So one of the problems, for instance, with image velocimetry is that if it's raining really hard, you're not going to get a good image. Or if it's at nighttime, you're not going to get a good image. So that's where something like a side-mounted ADVM would be a better candidate. One of the benefits of this is you're actually getting velocities across the whole section of the river. So when it does work, you're getting a more thorough understanding of the velocity vectors.
Okay.
Another good method is your surface velocity radar as well. That's another instrument we're looking into. And actually, if you look on the image, we've got a radar mounted on the bridge that's looking at the velocity of the water.
Okay, very cool. So yeah, there are a few more questions, but hopefully those folks can contact James directly. I'll just take a final moment to say thank you so much to all of our speakers for the excellent presentations. I found them really interesting and practical applications of different techniques that we can use in hydrology. Thank you so much to our audience for attending and for all of your questions. I'm sorry we couldn't get to more of those, but I really appreciate the interest that we had in this webinar. So thanks so much, everybody, and have a good rest of your afternoon.
Thank you.
Thanks.